Now I'd just like to look at some of the problems from section 6.2. Here's one, number 15. So we're given a vector and another vector. We want to find the distance from y to the line through u and the origin. So let's just draw a picture here. So we have y that's going over 3 and up 1. So this is the point that we're interested in. And then we have this vector u, which goes over 8. Let's see, 4, 5, 6, 7, 8, and up 6. So 2, 3, 4, 5, 6. So over 8, 6. And the question is to find the distance from the end of this vector to this line. So the distance would be orthogonal in there. So what I'm going to do is I'm going to figure out, I'm going to write y in terms of a scalar multiple of u plus some vector that's orthogonal to u. Then I can find that vector z is going to be y minus alpha u, and the distance would be the length of z. So I'll just calculate the length of z, which is going to be just the length of y minus alpha u. Okay, so the way we figured out what alpha was is we dotted both sides by u, and since z was assumed to be orthogonal to u, it disappeared. So we got that alpha was going to be y dot u divided by u dot u. And in this case, y dot u is going to be 24 plus 6, that's 30. And u dot u would be 8 times 8, that's 64, plus 6 times 6 is 36, so 64 and 36 is 100. So alpha is actually 3/10. Okay, so that tells us that alpha u is 3/10 of u, so we would have 3/10 of 8, so 3 times 8 over 10, and 3/10 of 6, so 3 times 6 over 10. And let's see, what does that give us? So 2 will go into 8 4 times and into the 10 5 times, so we really have 3 times 4 over 5, so 12/5. And one of these 2's will cancel, I'll have 9/5 for alpha u. Then to find z, I'm just going to take y minus alpha u. So 3 is 15/5 minus 12/5 would be 3/5, and 1 is 5/5 minus 9/5 would be negative 4/5. So that's my vector z. Now I should just check real quick, because z, if we've done it right, if we've calculated alpha correctly, z should be perpendicular to u. So I'm just going to quickly dot that with u. If we dot u and z together, we get 24/5, because 3 times 8 is 24, but 6 times negative 4 would be negative 24/5. So yeah, z is perpendicular to u, z is orthogonal to u. So it seems like we've calculated z correctly. The last thing to do is just to figure out the distance. Since this is the vector z that's projecting y onto u, that's the perpendicular distance from this point at the end of y down to u. So the distance is just going to be the magnitude of z, which will be the square root of 3/5 squared, that's 9/25, plus 4/5 would be 16/25 if I square that. So that's the square root of 25/25. So the distance between this point in the plane and the line that goes through the origin and this point is equal to 1. Okay, here's another problem. Says true or false, so we want to give reasons for our answers. The first one says not every orthogonal set in Rn is linearly independent. So we did have a theorem that said if you had a set of orthogonal vectors, it would be linearly independent, but it assumed that they were non-zero vectors. So you can have an orthogonal set, and if one of the vectors is the zero vector, it's orthogonal to everything, so that's okay. But having the zero vector in your set means that it's not going to be linearly independent. So it says not every orthogonal set is linearly independent. Yeah, that's true, right? Because you could just take this set 0 with some other vector, and this is an orthogonal set because the dot product of every possible pair, there's only one possible pair, is a zero vector. So it's an orthogonal set, but it's not independent. So we'll say that statement is true. Okay, now if we have a set and it has the property that ui.uj is equal to 0 as long as I is not equal to j, then that means every vector is orthogonal to every other vector, then it's an orthogonal set. And we say, yes, that's true. Okay. That was really the definition of an orthogonal set, right? And C, if the columns of an n by n matrix A are orthonormal, so that means they're all perpendicular, mutually perpendicular and have length 1, then the linear mapping x maps to ax preserves length. Yes, that's true by theorem 7. Okay, D. The orthogonal projection of y onto v is the same as the orthogonal projection of y onto cv whenever c is not equal to 0. So remember, if we wanted to project it onto v, we would assume that y was some scalar multiple of v plus a vector that's orthogonal, and then we dotted both sides with v. Got alpha v dot v. Z dot v, since z was assumed to be orthogonal to v, we assume that that's 0. And solving gave us alpha equals y dot v divided by v dot v, and therefore the projection alpha v was going to be y dot v over v dot v times v. Now if we take y and we assume that we project it onto some scalar multiple of v, and we could dot this with v as well, and we would get y dot v equals alpha c v dot v plus 0, because z is assumed to be orthogonal to cv, or orthogonal to v, orthogonal to cv, and therefore orthogonal to v because they're scalar multiples of each other. So we would, again, this time we'd get alpha is equal to y dot v over cv dot v, but the projection would be alpha cv, so we would have y dot v over cv dot v times cv. And since c is just a scalar, it's going to cancel. It's going to give us exactly the same thing as we had before. So this is true. So kind of makes sense, right? You're just finding how much of this vector y lies along the vector v. So if you stretch v out and make it longer, say, it still casts the same shadow onto that longer vector cv. So it shouldn't matter whether we project onto v or c. And this last statement, an orthogonal matrix is invertible. Let's see. It's not invertible in the usual sense. Because an orthogonal matrix might not be square. Okay, so that's false. For us, for a matrix to be invertible, it had to be square. Okay, one last problem from section 6.2. Suppose W is a subspace of Rn that's spanned by n non-zero orthogonal vectors. Explain why W is actually the whole space. Well, because orthogonal vectors, non-zero orthogonal vectors, are independent. So W is the span of n independent vectors, so W must be an n-dimensional space. But it's a subspace of Rn, so it must be all of Rn.